Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Welcome to the show, Boaz. Great to have you with us.
Thank you very much, Ryan, for this opportunity. I'm very pleased to be here and talk about what we do in Tactile Mobility.
Great. So maybe if we could just start out with, sort of understanding your background, where you're from and how you came to be doing what you're doing now.
Great. So I'm a technical guy by essence. This is my soul. Try to solve complex things system-wise. And entrepreneur. I try to start new things and convince people to come with me. That's what I do for a living for the past 50 years or more that I'm living. I have graduated electrical engineering, computer engineering in the Technion in Haifa, in Israel, a couple of decades ago. And then co-founded a company named Charlotte's Web Networks, designing terabit routers, like the big ones back then. And after several years and some success, I left the company and worked with Zoran Microelectronics, where I led the system team here. They're designing set-top boxes, chips, and the ASICs, main ASICs for television and other home entertainment equipment. And 10 years ago, I again decided to leave, the comfort zone and start a new company. These are the bugs that I already have in my mind. So 11 years ago, I started Tactile Mobility here in Haifa, and this is where I come from. Married, 3 kids. That's it. Happy life. Thanks God.
And just on, maybe a quick word on what got you started in engineering in the first place. What was the attraction back then? And I know I often say to people, we're kind of similar age, and science and engineering are much more popular now than they used to be, and particularly electronics and software and things. Back then, what sort of got you excited about that field?
Well, from the moment I remember myself, I was always fascinated about technology. We are talking about the early 70s. So the first radio I got in my hand, I disassembled it. The first computer that was issued to the market, if I'm not mistaken, it was ZX80 by a Sinclair company. So it was 1980. So I got the first computer. My father bought it for me. So I started learning myself software development. It was basic code and some more assembly code.
Yeah.
And that was my hobby for years. So I always did hardware and software and some mechanics and all the combinations between. So anything about it. Self-educated, I think, at first, until, I have graduated or completed my military service, compulsory service in Israel. And after that, I went to the academy, to the Technion. This is like the Israeli MIT, where I graduated and learned my hobby. That was my hobby. So far, thanks God, my hobby, my profession, and my making money comes from all the same thing. and I really say that each day that, I come to the office, I come to my work, I decide what I want to do and what I don't want to do. and I managed to sell it, to customers, to investors, to people with money, with the abilities, and convince them to follow me, to follow my steps, and then try to change the world. I mean, it sounds a little bit peculiar, but it is like this. I will give you a few examples later on.
Great. No, that's really interesting and great that you're sort of what I would describe almost as an organic engineer. It's just in your bones, in your blood, and it kind of got you going. That's fantastic. So moving into then the business, I mean, the first thing that caught my attention, to be honest, was the name, Tactile Mobility. And I was kind of thinking, what can that mean? Really interesting. And then kind of looking at some of the information that your team provided before this recording. It was really, really fascinating in terms of reading about what you do. But could you explain to us the company? You mentioned you started 10 or 11 years ago?
11 years ago, yes.
11. Okay. So how did that come about? Why did you start the business, and what is it that you do?
First of all, I don't understand in vehicles. So I didn't understand in vehicles until I started the company. And even now, there are basic things that I don't know because it's not my hobby. I mean, vehicles, are not my hobby. It's a profession today. It's my making money out of that, but it wasn't my hobby. So there were funny examples, like the first time I visited a Porsche company, and the engineers that provided me the first Porsche 911 to install with our aftermarket device. When they opened the hood, the first thing I ask is, "Where's the engine?" Okay, so I even
Okay.
didn't know that the engine is from the back. So this is my background, because I started with the design of communication systems, routers, and stuff like this, algorithms. Nothing has to do with mechanics or chassis handling or vehicle handling. I even don't own any fancy car. I have my old Mazda, which I like very much. I got it from my previous company as a leased car, and it stayed with me. And then today, even my rule of thumb is that everything I design must comply with my old Mazda. So I don't design fancy things for fancy cars. I design fancy things for old cars. So I want to aim for the plain vanilla of the world, to be in mass vehicles, not on high-end sophisticated vehicles with special hardware sensors inside. This is very important. So it all started when somebody came to me and gave me like a puzzle, a riddle. Okay, he said, "I want to deliver a vehicle from point A to point B with minimal fuel consumption. Can you help me do it?" I said, "For sure. Let's analyze what is the performance of a vehicle in terms of fuel consumption per configuration, per gear position, per load, etc. And let's analyze what is the surface condition, like road grade, inclination, banking, curvature, etc. And then combine the two to provide the best profile of driving to allow the vehicle to reach its target with minimal fuel consumption." So I started working on this like a part-time job because it puzzled me. And when I started working with it, I realized that the fundamental information is not there about the surface. You cannot retrieve a precise map of road grades today. Okay, so even if you look at Google Maps or stuff like this, it's like smoothing the surface. Okay, it's not the texture; it's just the surface. This is on one hand. And on the other hand, the vehicle themselves, nobody can tell you what is the exact fuel consumption rate per moment, per second. There are gauges, there are ways to measure it, but it's off like 30%.
Yeah.
So if I want to save 5% of fuel consumption, and the noise flow of my system is 30%, then how can I do it? So the project turned into building the building blocks. So let's first measure the exact performance of the vehicle in terms of fuel consumptions. What is my momentarily? fuel consumptions, okay, 100 times a second. So this is the first, actually the first virtual sensor that I've designed, okay? A virtual sensor, it's a software generating information very rapidly in a computer in the vehicle or an aftermarket device attached to the vehicle that is collecting the already existing noisy sensors that you have in the vehicle, the physical sensors, combining them together, fusing them together, and then out of that generating information that is missing to the, in this case, is the exact fuel consumption momentarily, okay? So that was the first virtual sensor. And on the other hand, for the surface itself, since nobody has the map of the road grades, the precise road grades in each meter of the road, then I needed to generate it myself. So I had my vehicle driving around, collecting information, out of that generating the information about the road. So as it developed along the time, the company is designing today these two types of information. One we call surface DNA, okay? This is the information that has to do with how the surface looks and feels. And the other one is the vehicle DNA. Vehicle DNA is the ability or the representation of the vehicle. It's also called in the industry as the digital twin of the chassis or the vehicle. So how to represent the vehicle in sets of coefficients, of lookup tables, of formulas, whatever, that out of that I can derive very precise information about my vehicle. For example, momentary fuel consumption, okay? Or my weight, okay, that my vehicle weight now, or my tire status, what is the stiffness of my tires, what is the tread-ups of my tires, etc. So these are all coefficients and numbers and values that you need to crunch and to represent the status of your vehicle, the vehicle DNA or digital twin of your vehicle. So actually what Tactile Mobility is doing today, at the end of the day, is providing a software. First of all, we are a software company, pure software, no hardware. We are using the existing hardware and preferably the low-cost hardware in the plain vanilla vehicles. So to be able to do with a mass, not with sophisticated vehicle. So in these cases, we provide a software for the ECU, one of the ECU, okay, engine units in the vehicle. And this ECU, having our software, is collecting existing sensor information from the vehicle, for example, wheel speed, torques, accelerations of different types, even GPS location, okay? And then crunch it, fuse it in real time, and then out of that, derive close to real time new information about the vehicle. And the information are of two types, information about the surface that we are driving on now, or about my state of my vehicle, my digital twin right now, about all these parameters. This information is represented as what we call virtual sensors, is you don't have a weight sensor in the vehicle because it's too expensive or not very accurate or something like this, but if you will have the tactile software inside, you will have a virtual sensor that will provide you the weight of your vehicle, estimation of your vehicle weight along the drive. So those virtual sensors are being sent back to the CAN bus, FlexRay, whatever. So all the other customer functions in the vehicle can use it for preconditioning of the chassis or for doing whatever you want with this information. In parallel to that, we expect the gateway in the vehicle, it's a connected vehicle, so to transmit this information back to the cloud, where we are collecting those outcomes, okay, those outcomes of the virtual sensors in order to generate maps of two types, surface DNA maps and vehicle DNA maps, okay? Surface DNA maps, for example, has layers like the grip estimation, friction estimation of the road, the distresses, potholes, bumps, etc., and road grades, inclination, anything that has to do with the tactile sensing of the road. And I will come to the word the tactile in a moment. Okay, so those maps that we have on the cloud side are refreshed map. Okay, very close to real time from millions of vehicles driving around. that can be monetized or can be utilized, okay, close to real time or periodically. Close to real time, you can provide it back to the vehicles as the horizon prediction ahead of them. So you will know, your car will know what's ahead of you in the next mile, like what will be the friction of the road there, what will be the distress situation, etc. Okay, the surface DNA of the next mile. And in parallel to that, we are monetizing this information for other segments like road authorities and municipalities, winter maintenance of roads, and other types of stuff like this, like, for example, insurance companies and anyone that needs this information. As for the vehicle DNA, this piece of information is very crucial for vehicle health predicting, maintenance, precondition. For example, if you know your tread depths, okay, you know when you need to replace the tire, or you know that you have a worn out tire, you know how to precondition your vehicle accordingly. For example, if you have an adaptive cruise control, maybe in such a situation of a worn out tire, you would like to keep a larger distance with the vehicle in front of you just for the safety. Okay, so those virtual sensors about the vehicle DNA can help you improve the ADAS and improve safety and efficiency of your vehicle, for performance and for safety. So in an essence, to make a long story short, Tactile Mobility is all about a software, a very sophisticated software that sits on the vehicle side, on the ECU, and is located on the cloud side, and both are generating meaningful information about the surface and about the vehicle.
So many questions. So on the and in the past, I've been involved in some projects doing things with data collection and such like on vehicles. And you mentioned a couple of things there actually that I know from experience are really, really hard. And I'm just wondering, is it because you're using a sort of fusion of different data streams, but like, for example, predicting the weight of the vehicle? I mean, that is a really tangible, useful thing that, commercial vehicle operators, for example, if they didn't have to, quite often they either have an expensive sensing system or they don't have anything at all. And predicting the weight of a commercial vehicle would be really, really useful. People would pay money for that. But it's actually super hard to do that, just using the data that you get from the vehicle. You sort of, in theory, you can say, well, I can imagine how I could do that by, I go a predicted rate of acceleration, and if I know that if I apply this much throttle, it should do this, but it does that instead. But there's so many variables that kind of have an impact on it, like the gradient, like wind speed, like all sorts of things. It makes it really hard. How are you getting around those kind of things? How can you get to a good, sort of reliable outputs for these things?
This is a few tens of millions of dollars question. The amount of money we raised so far. So actually, this is the kind of questions I'm used to get from the experts in the OEMs that I'm working with. I'm sitting in a Porsche 911 or a BMW 7 Series with the expert of BMW or Porsche or Ford or whatever. Okay, we drive the same test car. We have our screen with aftermarket device that installed there, and it shows them the precise weight of the vehicle or the friction coefficient with the road now. Okay, just by cruising on top of that, and they ask me these questions: how do you do it? We see the same signals that you do. Okay, we are connected to the same chassis canvas. We are collecting the same noisy signals, and indeed you're right. It's all contributing to, we call it noise. Okay, it's a noise if you don't know what it's doing. Okay, but it's not noise; it's an information. If you can correlate it with coefficients or stuff like this, you get information out of that. So this is what tactile mobility is all about, is to take the existing noisy low-cost sensors in the vehicles and try to extract the behavioral of the vehicle, the coefficients of the vehicle, and correlate them with each other and generate this information out of that, and everything is edge computed. In order to do it, we are utilizing Signal processing, as normally done in the industry. We're utilizing physical modeling, same, always used in the industry. However, in order to solve those mysterious second and third order of physics of those coefficients there, okay, what is my current, I don't know, wind drag coefficient, okay? What is my current wind drag coefficient? What is my current rolling resistance status, okay? So in order to solve those missing coefficients, we run machine learning, okay, internally in the ECU in real time to help us solve those equations and then get to those coefficients. If those coefficients are close to steady states, like quasi-static coefficients, I don't know, like a rolling resistance, maybe this is something that is changing a little bit slower than maybe a wind drag, you open the windows, close them, etc. So we save them in the non-volatile memory in the vehicle and fine-tune them a long time, right? And then at the end of the day, once the machine learning is outputting estimation, you need to filter that out in a sophisticated filtering and non-realistic results, okay? Or non-realistic is not just, outliers of minimum and maximum, but very, very sophisticated situations. So having a machine learning working at 70% of the cases or 80% of the cases is something very nice. But nobody will use it in the vehicle, okay? Even if it's only 99% of the time. When you're driving a vehicle, you want to know that you are safe, that you can do things, and you have a precise information. So the ability, I mean, the big secret sauce here, or the very good engineering, as I call it, is to be able to take those results, or machine learning results, following the physical modeling and the signal processing, and to extract out of it only those results that make sense and that you can guarantee and provide it outside. So the entire pipeline chain, let's call it, okay, that we have in real time in the ECU, this is what enables us to do what we just asked, like how we can know all the contributions of all, the factors there in order to reduce the signal to noise ratio and extract the data out of that.
I mean, that's a massive achievement. Does it take a long time to profile that? If you are doing, let's say you installed your system on a new vehicle that you hadn't seen before, does it require a certain amount of time to kind of learn the vehicle, or how quickly are you able to generate that those DNA models?
The first type is the general or generalized vehicle DNA model that stands for a specific series of vehicles. Okay, maybe BMW 3 Series. Okay, or maybe a vehicle that is I don't know, hybrid vehicle, for example, electric vehicle, etc. So for those types of vehicles, we have a generalized way of representing them, like the digital twin of the vehicle. And then on top of that, there is a part that we override with edge computed information, which we call my vehicle DNA. Okay, so the my vehicle DNA is part of the vehicle DNA that my specific car will actually calculate while driving, fine-tune those parameters, and override the existing generalized parameters of the vehicle DNA. For example, tread depths. Okay, so if you have tire parameters so you can think of that a new vehicle that will roll out of the production line will hold the baseline, let's call it, or the super duper perfect tires parameters. Okay, and now when you roll out of the production line, the edge computed software in the ECU will assess the current state of your tires, extract the parameters out of those calculations, and save it locally on the My Vehicle DNA parameters. And from this point on, we'll use that. Some of the parameters needs few meters to calibrate. That's it. So once you start off ignition, a key cycle, start driving, it will take us like a few seconds, and then we know we are on track. So everything is okay. We are calibrated, validated. We can start our estimation. Some will take a few tens of kilometers. So if you replace your tires with new tires, of course, we automatically identify it, that there is a new tire now that we didn't know before. So in this case, from scratch, it will take us maybe 10 kilometers of driving, normal driver driving, in order to assess the new parameters, and until then, we refrain from estimating some of the estimations.
It's quite a rapid process. The surface DNA models of the road, obviously that is going to be dependent by its very nature in terms of what you're actually driving on from a road point of view. Does it make a difference, that kind of interaction between the vehicle model and the surface model? I can imagine it's a bit of a chicken and egg.
Yeah, that's the main issue here, is that it's like a chicken and egg, because you fill the surface filter, let's call it, with your vehicle DNA, and vice versa. So the chicken and egg need to be separated. Okay, so what are the factors that the surface contributes? What are the factors that my suspension, for example, contributes, or my tires, etc.? So this is what tactile mobility is all about. We call that normalizing. So when we are talking about surface DNA, the data on the cloud set should be normalized. Normalized meaning that you need to have a language describing the surface DNA in a way that every vehicle can utilize it. Now, this is one of the first things we did at Tactile Mobility, is defining this tactile language. When think of the first guy that invented the digital video, I don't know, like 40, 50, 60 years ago. So he invented like letters of the language, which are the pixels. So a pixel it's a letter of the language, the visual language. Out of a few pixels, you have a macro block or something, then maybe this is a word, okay? And maybe a frame is a sentence, okay? And then now we have a few frames, we have like a movie, it's like a story, okay? So this is a storytelling using the visual language of the word. Now that we have a language, I can exchange this information with you, because the fact that we both can see each other now is because we have a language to describe what we see and to transmit it to each other, transmit those pixels. Okay, so you can see me and I can see you. Okay, now for tactile language, this is something totally different. Imagine a blind person sitting near the driver, feeling something with the vehicle. Let's say he's connected in some way to all the sensors of the vehicle. This is a blind person, and he needs to represent it, to represent what he sees to his friend. Okay, that sitting in a different car, another blind person, what to expect in the next mile or so. When you see a bump, for example, a speed bump, you can define it as a 3D bump, right? But how do you define it when you feel it? So this is what tactile mobility is all about. We have developed a tactile language that consists of a small letters, tactile letters. Each letter stands for a small physical phenomenon on the surface that you feel. That if you combine those letters, you can now represent the essence of the surface. For example, a bump is a combination of few letters. I encounter the bump, okay, start ramping on, maybe I skid a little bit on the top, and then I ramp down, okay, maybe there is a small pothole right after that. So I will have few physical letters or tactile letters that will describe this precise speed bump, and they will identify it or distinguish it from another speed bump, okay? So this is a tactile representation of the surface DNA. Now, this tactile representation of the surface DNA goes through normalization process. We normalize it with the parameters of the chassis, with the digital twin, okay, or the vehicle DNA, and then we get a nominal representation of the surface DNA using our tactile language. Now, this is a unified map for the entire world, and we don't care if there is a truck that, actually mapped it, or a light vehicle, or, a battery vehicle, okay? And then this representation is now transmitted back to the vehicles, and then they go through a denormalization process so to understand what this bump will do to my car when I will drive on top of that.
It's something like mapping a bump in the road with a standard sensor set on a vehicle or an ECU. I mean, I can imagine you're going to need to know it's this sort of the vehicle DNA needs to be reasonably clear so that you know what the response should be, and then you can read the response, with the acceleration change in the vehicle or what have you when it hits the bump. But then, do you need then to start with a basic surface DNA in order to then map the vehicle DNA to then go back and start to map more complex surface DNAs that you haven't encountered before? Or are you able to do it sort of in parallel?
It's actually a mix of both. The first thing we start with when we are generating the vehicle DNA, okay, like for the family of the vehicles, is that we go through a calibration process. This is the same exact process that every tier 1 or OEM or tier 2 goes through with new vehicles in pre-production phases when they calibrate their machines there. So let's say Conti or Bosch, they have their own ABS or ESP system they sell to the OEM, right? Now you need to calibrate it. So even though that this model is being working for, I don't know, millions of kilometers already, but this is a new vehicle, we need to calibrate it for, and it takes some months. Normally it takes some months, few months, in order to calibrate this already working component in a new vehicle. Same for tactile mobility. We take our software, this is a software, okay, this is not hardware, but we take the software, we plug it into the ECU, pre-production-wise, and then we take a couple of test vehicles, and now we are defining what we call test maneuvers or calibration maneuvers. So those calibration maneuvers are actually defining the basics of the tactile language for this specific type of vehicles. Okay, so this is what we start with. Second, when this software is installed already in those vehicles and it goes out of production line, or if earlier if we have larger test fleet of hundreds of vehicles, then we are fine-tuning, okay, those tactile representation of how this vehicle feels the world according to the performance of those hundreds or thousands of vehicles, okay? So we have sophisticated the mechanisms on the cloud side for tactile mobility where we collect all these recordings from those vehicles and then crunching it continuously, generating those maps, and one vehicle helps the other vehicle to identify what they see there. Okay, so if I have a better vehicle that is now more calibrated, and I go through one bump, and then I go another vehicle there that is not calibrated, so I can, and so this is the chicken and the egg, okay? So I take the chicken from one car, and then this is the egg for the another car.
And the ability to sort of share that data in the back end. You can sort of start to piece together lots of different potential, applications or reasons why people would pay money to have this data. And I know in your information pack, you've got some things about the types of companies that you work with, but maybe if we could just, talk a bit about that in terms of who your customers are and how people are realizing the benefits of this in practice.
So we have two types of customers. Okay, one type of customers are OEMs or tier 1 selling to OEMs, where they have the tactile software inside their ECU, one of the ECUs in the vehicle. And then the customer, which is the OEM, enjoys this software normally by preconditioning the vehicle or the chassis with the information they get from tactile mobility. So now that they have tactile inside, it's like you have installed more sensors into the vehicle, okay, software-wise, and then you have new information that you can utilize to better perform the vehicle for safety or for performance, okay? So for example, like I gave you, if I can now have a sensor in the vehicle detecting the friction coefficient between my tires and my surface now, okay? maybe I can precondition the adaptive cruise control distance. If this is a low mu situation and icy conditions, then I will keep maybe 3 seconds, okay, with the car in front of me. If this is high mu situation, then maybe I'll keep 1 second. Otherwise, a lot of cars will take over and I will start driving backwards. Okay, so this is one example. So you can precondition suspension if the road is bumpy or not. You can precondition a suspension even with my tire status. Okay, if you can precondition your ABS to better detecting the slip ratio of the vehicle for the best operating condition of braking. So you can do a lot of stuff with that. This is one type of customers, which is the OEM. The other type of customers are utilizing the data on the cloud side, either in real time or offline. Okay, so in real time, we're talking about horizon prediction for vehicles driving around, and we are now in the integrations and discussions with customers about that. We have a lot of pilots with municipalities around the world that we provide from those vehicles that we already installed there and driving there, like normal vehicles. We provide information for road maintenance, either in real time, like winter maintenance, when to follow the snow or spread salt or something. And on the other hand, if you are planning for resurfacing some roads and you need like standard road conditions, detection in order to prioritize resurfacing of roads, it's a lot of money. Then you can use our reports for that, or even rapid maintenance. Let's say that you have no indication for potholes on the roads, but not a pothole as a camera will see that, but the pothole as the chassis feels it. Okay, this is more important than to see it, because the maintenance of the road will normally be according to the severity of the actions that will happen to the vehicles there. So if this is a severe port in terms of having a flat tire or something like this, then I will maintain it first.
And for that kind of the municipality scenario or that maintenance scenario, is that dependent on having a lot of vehicles, sort of public data, or could like say, for example, a local authority install their own vehicles and have a small number of vehicles gathering data, and it would give them a useful metric? Like, how would is it dependent on mass data collection, or can you have a smaller fleet?
So it's both. So some cities we already installed in commercial vehicle, like today we are installed in BMW production line, and we are on the verge of signing new contracts with other OEMs now. So we would like to have those commercial vehicles, getting the normal public information for the road authorities. And with road authorities that we don't have too many public vehicles going there, then normally what we do is that we have an aftermarket device. It's like a simple telematic device that is connected to the CAN bus in the vehicle, but it runs the same exact software that is in production in the ECU. Normally, those vehicles are either rental vehicles that, like a car to go that you take on the major cities, or taxi cars, or even municipality owned cars, okay, like the sheriff car, for example. I've installed the sheriff cars in the US that they collect the data. In this case, you need very few vehicles, maybe 10, maybe 20, 30 vehicles, even for large cities, big cities like Detroit, for example. Because the way or the nature of the tactile mobility software is that we have very high availability. Okay, so for example, when we drive, you will get every 100 or 200 milliseconds, you will get a precise information about the surface. So you have tons of data even from a single car. So a single car with a single path, because we reduce the signal to noise ratio, can generate a lot of meaningful information. You don't need too many cars to pass there too many times.
And the other kind of type of user where I can imagine a benefit straight away is kind kind of trucking fleets, commercial vehicle fleets, which you just mentioned there in passing, but that kind of some of the things that you're able to collect or at least indicate, like tire tread depth, tire pressure, tire condition. In some countries that, by law, they have to be monitoring that kind of information. And a good logistics fleet wants to know that information because it's not very productive having a vehicle stranded with a blown out tire. So, are you working with that kind of customer as well in the aftermarket? And could your data be used to really do that sort of prognostic analysis on a commercial vehicle like a truck?
In Tactile Mobility, we started as an aftermarket company. This is how the company started. So my vision was to have a telematic device, normally off the shelf or that will design it, but the software inside will be very sophisticated software to give meaningful information, right? One of the information, for example, tire information. The issue with that was that we couldn't find a good ROI for that, return on investment. Why? Because telematics was too highly cost, and not everyone would like to pay for that, for those features. And anyway, they will have other telematic device for, I don't know, for theft prevention or whatever, like geofencing. So it was like yet another telematic. So this is how it all evolved into OEMs. So to be in millions of cars and not in thousands or hundreds of cars of fleets. But anyway, this precise information that you get from the production line can be used for fleets. And this is what today we're working with OEMs. So as you know, some of the OEMs are producing vehicles for fleets, for large commercial fleets like rental companies, like FedEx, I don't know, robo-taxis or stuff like this. So it's a commercial fleet, but it is originated by the OEM. So in those cases, if you are already inside the ECU in the production line, so the major customer that will enjoy it will be these heavy commercial fleets, okay? But they will enjoy it not through an aftermarket device, but through the production line, okay? Which is much cheaper than they have today with telematics. One more remark, maybe interesting remark, like a few years ago, a delegation from a major tire manufacturer landed in my office. They said, you didn't answer my email, we want to speak with you. I said, okay, so what's the issue? And then I learned that everybody today from the tire industry are working on designing what they call smart tire sensor, okay, which is like a small piece of software that you plug inside the rubber, okay, that actually almost touching the surface and transmitting wirelessly into the cabin some informations and the conclusions that they collect there, okay? Now it's a very nice device. It can get into conclusions, for example, about tire wear, okay? But it's too it's too expensive, okay? So to pay like a few tens of euro or dollars per car in the production line, it won't get into production. And if you want to go to fleets, it's very complex to install it and to do that. So they asked me, can you do that virtually? So can we have a virtual sensor, like a software that is generating from the existing sensors we have in the chassis, an indication about the tire status? And this is what Tactile Mobility is all about. This is what we do today. So today we assess the tread depth without any additional sophisticated sensor. And this is the value for that. And this is why we don't need to go to the aftermarket and sell them some devices or stuff like this.
And I mean, I can imagine on a car or a van that would be effective. Maybe on a larger vehicle like a truck, it might be harder to do. But on a car, like, can you be specific in terms of, is that characterization quite general, sort of in general, or can you say like the front left is doing better than the front right? What's the kind of granularity of the data that you're able to map out?
So this has to do with the vehicle DNA. with a chapter or a section of the vehicle DNA that has to do with the tires. In this case, it's per tire. So per tire, we identify its reset situation, let's call it, okay? Like when we identify that there is a substantial change of the parameters, we know that this tire was replaced. Once it is replaced, we follow this tire, we analyze it. Some of the parameters might take a few tens of kilometers to analyze, but they change very slow, so we don't care about it. And some of the parameters are very, very rapid. Okay, like in a few seconds, we get to the parameter. So there are maybe 10, 20 parameters about each tire that we are generating and collecting. Okay, everything is edge computed. It is stored in the vehicle non-volatile memory, in the EEPROM, and then it is transmitted from time to time to the cloud. So in this case, you can get indication either in your infotainment, okay, or on the cloud side for the fleet, okay, to maintain those tires, for example. You do have today a TPMS in your vehicle, tire pressure monitor system, which can be direct or indirect, like specific hardware or by estimation, right? But you don't have a replace tire indication. You have inflate your tire, but you don't have replace the tire. So we believe that once Tactile Mobility prove it, and maybe other competitions will do that as well, they will prove that you will have a good enough indication of tire replacement rather than tire inflation, deflation, then it will be like a must-have. So everybody will must have such a sensor in the vehicle, indirect sensor, because it's cheap, it's a software, okay? So it's not a burden too much on the customer, the end customer, but the safety will be much dramatically improved.
And again, general public, that's one thing, but where you've got things like delivery vans or municipal vehicles or whatever, it's really, if it's a working vehicle, that's really important because it's well, they get abused more.
Yeah, right. And even with electric vehicles, as we all know, electric vehicles they tend to generate faster torque changes on the wheels. Okay, like the motor is faster than the combustion engine. So in these cases, there is like a 30% normally of tire wear higher in electric vehicles rather than in normal combustion vehicles. So you need to know with your electric vehicle what's the status of your tires.
And then, so the other business case that you mention in your literature and things is with insurance companies, and is this because it's so in the UK where I'm based, it's becoming more common for young people to have these kind of black box sort of monitoring systems in vehicles, basically Big Brother is watching you to make sure they don't do anything naughty. Are you providing that kind of service to an insurance company for sort of driver performance tracking, or is it something? Yeah, okay.
Simple and short answer: no.
Okay.
Yeah, I tell you why. Because I personally don't like it.
Okay.
I don't like to be the big brother to watch somebody behavioral. And I can tell you that one of the biggest rental companies that we work with, they asked us if we can provide them information about unclaimed damage. Okay, so those young kids that will take the car to go, they smash it in a way that nobody will notice it from the anger or whatever, or mishandle it. And then, like, only after 2 or 3 days, they will find out and nobody can be claimed for this damage. Now, we have the technology to do it. We can identify a severe change of the vehicle DNA by handling it, okay? So if there is a change in the vehicle DNA, we can notify. However, the management of this company decided that if they will have this big brother sophisticated technology, so these young customers will, switch to another competition company. So this is why I don't like it. But nevertheless, there is an information that is crucial for those companies or insurance companies that's not related with driver behavioral, but either with the vehicle DNA and surface DNA. And I can give you 2 examples. Okay, so if you have like statistical situation of roads in a country or in an area, then those companies, insurance companies, can assess better the prediction, of troubles or damages to vehicles on those areas. So you cannot, no need to average, the expected cost of all the vehicles on one each other. This is one thing for using surface DNA for better predicting losses for insurance. The other one is, think about it. If you want to investigate an accident, okay, to know what led to this accident, or what was the reason, the cause, or what happened there, and mainly on severe accidents, you would like to have like a black box, okay, like you have in an airplane, okay, like a black box that will record everything. But what you record there is what was the situation of the chassis, okay, at the same time, and of each of the components, and what was the performance of the chassis at that time, okay? So is it the cause of my tires, okay, they were worn out so I couldn't brake, or maybe I didn't try even to brake, maybe I steered a little bit, maybe something happened to my tire before. So all this information that will lead to a very clear investigation about the causes of a severe accident. These are like two examples of what vehicle DNA and surface DNA can help insurers, rather than framing your young daughter that will travel.
It's been really interesting, I'm sort of conscious of the time it's flown by, but I've been enjoying kind of learning more about what you're doing today. I guess to sort of bring things to a conclusion, you've mentioned a couple of times about sort of autonomous or robo taxis or whatever, and the question that's on the tip of my tongue is about how this technology might be used in the future, and particularly in the context of more autonomous vehicles. But yeah, so what do you see in the future? Where do you see the company going? What sort of applications do you see coming through in the future? And what's got you excited?
Right. So we have analyzed, I think, this the future like a few years ago. We anticipated that fully autonomous vehicles will not be in the near future. Okay, and I think that today people already realized it, and the people today are talking more about the level 3. Okay, which is like something in between. It's more like evolution rather than revolution. So we are focusing on the needs of level 3. So friction estimation, preconditioning of the chassis, everything is very important for that. As for the future, today, like 90 or 99% of the companies working on sensors for vehicle are visual sensors. When I say visual, it can be radar, LiDAR, camera, of course, infrared, ultrasonic. These are all pixels, different ranges, different wavelengths, or whatever, okay? Maybe the pixel represent heat, maybe it represent a distance or color, but it's all pixels, it's all visual. This is 99% of the perception that people today generate in the vehicle, and even think about it for the future, fully autonomous, is visual. However, imagine yourself try to drive your own vehicle remotely with visual only. It's like a remote control driving with the screens, and you have a joystick or a steering wheel, etc. And then let's say that you even have a zero delay with the vehicle. Okay, I claim that you cannot drive it, not fast, very fast, not with the other cars around you, especially not in winter situation or slippery roads, and especially not if your kids are sitting on the back seat. Why? Because visual is not enough. You need to feel the car. You need to feel the vehicle. You need to feel the surface. Maybe it's only 1% of the information on top of the visual that you need, maybe 5% of the information. But this small piece of missing information will make it impossible to drive fully autonomous vehicles with visual only. This is why we claim that every autonomous vehicle will have those visual sensors as well as tactile sensors. And what we do now is that we form this tactile sensor in the vehicle. Okay, this is why we call our software tactile processor. Okay, it's not a grip sensor, it's not weight sensor, it's a tactile processor. Like you have a video processor, you will have a tactile processor. I'm sure we'll have tons of competition in the next few years. Hopefully, we'll be ahead of everybody and be in millions of cars by then.
It's really interesting, and I can really see what you mean there. Driving a vehicle, a bit like if you've ever tried to fly a drone with visual only, or play with your kids' remote control.
You know that by FAA rules, you cannot drive a Boeing, for example, or Airbus over the ocean if you don't have several ways of navigation. So it's 99% of the time it will be GPS. But if the GPS fails, you need to have the beacons, or I don't know, other means of navigation. So nobody will let an autonomous vehicle drive with visual sensors only, even though like 99% of the time they will rely on the visual stuff. Okay, but you will always need the tactile one to assure it.
Yeah, cool, brilliant. Well, that's a really good point to bring it to a close. It's been absolutely fascinating. Thank you so much for taking the time out to talk to me today, Boaz. It's been really interesting.
Thank you very much, Ryan.